All right, so this is going to be part one of the lesson on exponential functions. And basically in this part one, we're just going to look at some basic ideas of what exponential functions are. Now, in previous lessons, you graphed what was called polynomial functions. All right, so polynomial functions. And an example of a polynomial function that you graphed was something like this: f of x equal x squared minus 3x plus 4. Remember, that was a quadratic function. That was a quadratic function. And you graphed that in somewhere in chapter 3. Okay, so that will be a polynomial function. So remember, polynomial functions, the terms, each of the terms has this form. So the term has the form a times x to a power, and this exponent is a whole number, okay? So like 0, 1, 2, 3, and so on, whole numbers. And so notice that when you look at, and a can be any real number, rational or irrational, but n must be a whole number. Cannot be negative, cannot be a fraction, okay? Must be one of these numbers. And so notice that in each of these terms here, your exponent's 2 here, your exponent's 1 here, and then you have your constant, okay? All right, now, another example of a polynomial function is this: g of x equal x cubed plus 7x. So remember, this is a cubic function. All right, but notice it still has that form right here, where each of those terms, the exponent is a whole number. Okay, 3, 1. All right. Okay, now, so those are polynomial functions in terms of the expression. That's what it looks like. Now, an exponential function. Here's an example of an exponential function, and then we'll explain the difference. So an exponential function, here's an example: f of x equal 5 to the x power. Okay, 5 to the x power. So I want you to notice something here. See how these exponents here were whole numbers? And if you consider this your base, the base was the variable. Okay, look at this right here. It's just the opposite. It's just the other way if you want to look at it in those words. The base is a constant, okay, is a number, a real number, and the exponent contains the variable. So in an exponential function, one of the things you can remember is that the exponent is a variable expression. Okay, so the exponent contains a variable. The base is a real number. Okay, so that's the difference. All right, so for example, so if you look at this, these would be other examples of exponential functions. F of x equal 2 to the x minus 1 plus 3. See how the exponent contains a variable. All right, this is your base. The base is a real number, 2 in this case. G of x equal 7 times 2/3 to the x power. Same thing. The base is a real number. Your exponent contains a variable. All right, so these are exponential functions. The graphs look different, and so we're going to talk about that at some point. Okay. Now, before we do that, though, we need to be able to use our calculator with these exponential functions. So when we look at graphing, you need to be able to approximate some y values for a certain x value. Okay, so let's talk about how to use a calculator. So the next thing we're going to look at is the using a calculator to evaluate expressions. Okay, so let's look at this. So find each of the following. Right, so we're going to start with an easy one, just making sure you know how to use your calculator. So the first one we're going to look at is this one. So 2 to the third power. You all know what that is. That's 8, right? And you all know how to use your calculator with this. So you're going to say 2 raised. So you're going to use this right here. All right, so 2 raised, see how it shows up? 3 equal 8, right? Okay. Number 2, suppose we had 2.6 raised to the second power. Same thing, right? You're going to say, all right, now we may have to approximate this. We'll see. So 2.6 raised to the second power gives us, so that'll be 6.76. Okay? All right, number 3. So far, no big deal. You can handle that. All right, now let's look at number 3. Suppose I had 4.6 times 2.7 raised to the second power. All right, let's see what that is. So in your calculator, you're going to say, just as you read it, you're going to say 4.6 times, in parentheses, 2.7 raised to the, see how that looks, raised to the second power. Press equal, and you get exactly, I'm just going to write out what is exactly equal to, 33.534. Okay? All right, now number 4, let's suppose we had 2 raised to the square root of 3 power. Okay, so that's where we're going to start looking at some irrational numbers. See, all these so far were rational numbers. 8's a rational number, 6.76 is a rational number, 33.534 is a rational number, right? And the reason is because 4.6 is rational, 2.7 is rational, and so if you look at all, a rational number raised to a rational number is rational times rational is still rational. But here we have an irrational number, so we're going to have to approximate this. All right, so here's how you can do this, though. So I'm looking at square root, so you're going to say 2 raised, all right, I'm going to find my square root function. See, it's right here, see it? So second square root, see what that looks like? Okay, and then we'll press 3, close the parentheses, press equal, and so notice this is an irrational number. So you have no, remember an irrational number, there's no repetition of digits at all. Okay, so, and it doesn't terminate, so we have to approximate to, let's say, 2 decimal places. So let's make it 3 decimal places. So 3.322, right? So the thousandths place. So since this is 5 or bigger, this becomes 2. All right? Okay, number 5. Suppose I had 2.6 raised to the negative 1.3 power. All right, so again, let's see what that looks like. All right, so we're going to get 2.6 raised, in parentheses, negative 1.3, close the parentheses, press equal, and I get approximately 0.289. Okay, 0.289. Actually, that's what you got. All right, number 6. Let's suppose you had, let's see, I'm trying to get one that's similar to my math lab. All right, and then just one more. I think this part's okay so far. So let's say we had 3 to the negative square root of 5. All right, so let's see what that is. So we're going to say 3 raised to the, right here, in parentheses, negative square root 5, close the parentheses, close that, because remember you had 2 sets of parentheses, you see that? So I closed the 5, and then I got to close that exponent. Press equal, and you get approximately 0.086, okay, thousandths place. All right, okay, now here's something else when you look at, though, a very important, remember we talked about these bases here. See, this base is 5, these of the exponential functions, this base is 2, this base is 2/3. There is an important base that shows up quite often in business applications, science applications, and math, and it's used quite often in those courses. And that's the base, and we're going to talk about that. So we can look at base E. Base E. You may say, E, what is E? Well, we're going to look at that. All right, so base E. So E is a number. E is a number just like pi is a number. So E is a number just as pi, remember pi in geometry, is a number. Okay? Now remember what pi measures in geometry. So pi, remember, if you look at a circle, any size circle in geometry, whatever the size circle is, okay, and you look at the diameter, remember the diameter is a segment that goes through the center, and there's an infinite number of those. No matter what size you look at, okay, it turns out that if you look at the circumference of each of those circles, remember circumference? Circumference is the distance around the circle. So if you look at the circumference and you divide that by its diameter, for all these circles, that ratio is the same number. And that ratio, that number, is equal to pi. That's what that is. So that's where pi comes from. So pi is just the ratio of the circumference of a circle divided by its diameter. And it turns out that pi is an irrational number. Remember, you can't irrational number. All right. So meaning that it's not rational. Okay, not rational. And remember, a rational number is a number whose ratio of integers, just as long as the denominator is not 0. Okay? All right, and it turns out, you remember, that pi is irrational, so there's no way you can write pi as a fraction where you have a integer divided by an integer. And remember that pi, we approximate that to 3.14. All right, now, remember there's an infinite number of digits behind that. We just remember 3.14. It's just an approximation of pi. The same idea with E. E is an irrational number as well. That's an irrational number. Okay, and if you look at your calculator, there is an E button in your calculator, and we can get to that in a little while. So there is an E button in your calculator. So you may say, well, what is E? Well, E is used quite often in business, especially when you're talking about compound interest. It's used in some of your science classes. You'll see that in some of your science classes, the number E, and engineering, and it's used in most of your math classes when you get past college algebra. Okay, so let's talk about what E is. All right, now listen carefully to this part. So E is called Eulers number. Okay, Eulers number. So it's pronounced Euler, not Euler, Euler. Okay, so Eulers number. And so the number E is one of the most important numbers in mathematics. And notice that here are some of the digits. There's an infinite number of the digits. And notice that it looks like 182. You see how 1828, 1828, the first few digits starts repeating? It doesn't occur anywhere else. So that's one of the few irrational numbers where it looks like repeats, but it doesn't. All right, so it's actually an irrational number. There's no repetition, there's an infinite number of digits, and so on. But I'm going to just tell you right now, we approximate this. Let me just tell you, we're going to approximate this to 2.718. That's what most students remember. That E is approximately equal to 2.718. So that's what we use. Okay? All right, so E is often called Euler's number, and it's an irrational number, so it cannot be written as a simple fraction, meaning a ratio of integers. Okay, cannot be written as a ratio of integers. Now, when we talk about logarithms soon after this, when we talk about logarithms, you're going to see that E is the base of a natural logarithm. So we're going to come back to that idea later, all right? But E is the base of a natural logarithm. And so E is found in many areas that I mentioned earlier. Okay, now let's look at this part. So you may say, well, where did E come from? How do you know that E is approximately equal to this? All right, well, for you, you're just going to memorize that, right? You're just going to say E is approximately equal to 2.718. But here's where it really came from. So Euler, so there are many interesting ways of calculating the value E, but none of them ever gives a total exact answer because E is irrational. All right, so we just approximated to 2.718. Okay, now in calculus, when you get to calculus, you're going to see this expression right here. So it means something. You're going to see it later on. But here's the idea. If I take, see this expression? So if I take the number 1, right here, 1, and I substitute 1 in place of n, do you see you're going to get 2? You can put that in your calculator. So look. So you're going to say 1 in parentheses. You're going to say 1 plus 1 divided by n is 1, right? All raised to the n power, which is 1, and you get 2. You see that? All right, let's do 2. If n is 2, I get parentheses 1 plus 1 divided by 2, close the parentheses, raised to the second power, equal, you get 2.25. See that right here? All right, if I go further down, so let's say 1,000. So if n is 1,000, notice what happens. You see that all of these values right here of this expression is 2 point something. You see that? Is it ever going to be 3 or 4 or 5, this expression? Let's see. All right, let's see what happens. Okay, so let's say n is 1,000. So you're going to say, in parentheses, 1 plus 1 divided by 1,000, close the parentheses, raised to the 1,000, and you get this number right here, 2.71692, and so on, right? Okay, do the same thing with 100,000, you get that. But notice that as you get bigger and bigger and bigger, you see how it's kind of leveling off right here? You see that? So this was 2.71692. This was 2.71. See how these digits here are the same? Right here. And then it starts leveling off. See how it starts leveling off? So if I put, let's say I put 1 million. Go ahead and do that. Let's see what happens. Let's see what that is. So if n is 1 million, we get, in parentheses, 1 plus 1 divided by 1 million. So you need 6 zeros. 1, 2, 3, 4, 5, 6. Raised to the 1 millionth power. 1, 1, 2, 3, 4, 5, 6 equal. And that is 2.718280 and so on. So it starts leveling off. You see that? You see that? So what happens is this. As n gets bigger and bigger and bigger, as n gets bigger and bigger and bigger, this value gets closer and closer to that number e. And so this value gets closer and closer to a certain value, and that's the number e. All right, and so e is approximately equal to 2.718. So if you put 500, if you put 5 million, 10 million, 1 billion, 2 billion, and so on, it's going to be close to this number right here. They will always stay around this number. So in calculus, though, you're going to learn this. So you're going to learn this idea. You don't have to know this. You do have to know that e is approximately equal to 2.718, though. That you have to know. But in calculus, you're going to use the idea of limits. So the limit as n approaches infinity. See how n is getting bigger and bigger to infinity? Okay? Of that expression, 1 plus 1 divided by n raised to the n is equal to e. That's what that is. So as n gets larger and larger and larger and larger, that expression is getting closer and closer to the value of e. Okay? All right. Now, so here's e. So e is approximately 2.718, right? So there's e, and there's that expression right here. So as n gets bigger and bigger, you see that graph gets closer and closer to that value of e right here. Okay? All right. Now, so the other way you can look at e is this. So remember in a high school course, you may not remember this, but if you don't worry about it. But there's something called a factorial. And so if you look at this right here, this says 5 factorial. That's what that says. So it looks like an exclamation point. So 5 factorial. And 5 factorial, remember, means 5 times 4 times 3 times 2 times 1. That's what that means. Just like 8 factorial means I start with 8 and I go all the way down to 1. And I multiply all those whole numbers down to 1. So 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So this has a place in probability. So when you look at a probability section in one of your math courses, you may see that, the idea of factorials. 2 factorial means 2 times 1, right? Which is just 2. That was easy to figure out. Also, one of the things you learned in factorial was that 0 factorial by definition is 1. And then 1 factorial is also 1. So these two factorials have the same value. Okay? All right. Now, your calculator has a factorial button, so let me just show you how to get to it. Now, you don't need it for anything we're going to do in this course. Okay? I'm just telling you, just reviewing how to get your factorial, just in case you take a standardized test and there's a factorial idea on there. So basically, let's look at 5 factorials. You're going to press 5. You see where it says probability? I mentioned a while ago that this has parts to do with probability. So you're going to press P or B, probability. And you see you have these 3 things that show up. You want factorial. This is permutations. This is combinations. This is factorial. So you go to your factorial. You underline it. Press equal. See where it says 5 factorial? Press equal, and you get 120. And if you actually did 5 times 4 times 3 times 2 times 1, you get 120. Let's do 8 factorial real quick. So what do I press first? To find 8 factorial, you press 8. Where do I go? Probability. This shows up. Permutations, combinations, factorial. Go to factorial. Press this arrow to go to factorial. Press equal. And then press equal. And you get 40,320. Okay? But here's the idea, though. So Euler used this method right here. So he realized the value of E is also equal to this expression. And when you take calculus, probably the second calculus maybe, if you get that to that point, if that's part of your major, then you're going to see this expression again. So 1 divided by 0 factorial plus 1 divided by 1 factorial plus 1 divided by 2 factorial plus 1 divided by 3 factorial, and so on, is going to equal E. So notice that 1 plus 1 plus 1 half plus 1 over 6 and so on is equal to 2.71666. And if you kept on going, you would get something close to 2.718. All right, so that was just a quick idea of where E came from. All right, but what you need to remember is 2 things. You need to remember that E is approximately equal to 2.718. You need to remember that. Now, when you do your problems, though, when you start graphing functions that have E as a base, you're going to use your calculator Z. We're going to see how to do that in a little while. Okay, and you also need to know that E is irrational. That's an irrational number. So that's why we use the letter E, just like we used the letter pi, the Greek letter pi, for the ratio of the circumference to the diameter. All right, now let's go back. I'm going to go back to this page right here, and then we're going to do number 7. So this is going to be number 7. Okay, number 7. Okay, suppose now you want to find E to the second power. Okay, so let's see what that's approximately equal to. And I'm saying approximate because remember, E is irrational, so you're going to have an infinite number of digits. So you're going to approximate to the nearest thousandth. Okay, so on your calculator, let's find where E is. Okay, so remember a while ago we said that E was the base of a natural logarithm? So right here, so it says ln natural log. And you're going to see this in one of our future lessons. So when we talk about logarithms. So ln natural log. Right above that, do you see that? You say E to the x? It's blue, right? It's going to use this right here to get to it. Okay, so here's what you're going to do. So E to the second power. You're going to press second, and then ln button, and then that goes up, right? Okay, so remember, you can press second, ln button, that shows up. I want to raise it to what power? The second power, so you press 2, close the parentheses, equal, and 7.389. 7.389, so that's approximately equal to 7.389. Okay, number 8, let's suppose I had e to the 3.2 power. All right, e to the 3.2 power. All right, so e to the 3.2 power, again, you're going to press second, e, right? Okay, 3.2, close the parentheses, press equal, and that's what, 24.533, nearest thousandth. Since that's 5 or bigger, 3 becomes 4, so 2 becomes 3, so 24.533. So 24.533. 9, suppose I had e to the negative 6.23. Let's see what that is. So e to the negative 6.23. So you're going to say second, ln, that was you get your e, negative, remember, make sure you press your negative button, not a subtraction button, you're going to get a syntax error. 6.23, close the parentheses, press equal, and we get 0.002 to the nearest thousandth, 0.002, okay? And then 10, let's suppose I had e to the square root of 7. E to the square root of 7. So that's going to be approximately equal to. All right, so again, what do you press first? You got to press E, right? So you're going to go to second, E, ln, okay? Now I got to get the square root button. So remember the square root button. You're going to press second, x squared to get the square root button. See what that looks like? I'm taking the square root of 7, right? Close the parentheses, press equal. So 14.094. 14.094. Let's do one more with that. E to the square root of 10, let's say. All right, so again, let's see what you did. So let's see if you can do this yourself. Okay, so pause this video and see if you can do this. All right, now let's see what we get. So second, E raised to the square root, second, x squared, square root, and my radicand is 10. Close that parentheses to close up the radical, and then the exponent, close the parentheses, press equal, 23.624, 23.624, okay? And then let's suppose the exponent was negative, e to the negative square root of 3. E to the negative square root of 3. Let's see what that is. So see if you can do this yourself. Pause the video and then come back and see if you got the same thing, okay? All right, so second E. All right, now I need to do the square root, but before I do the square root, I got a negative, right? Negative square root, so you got to press the negative first. Negative. See what that looks like? Then I do the square root. Square root. See how that looks? Negative square root. My radicand's 3. Close that parentheses. Press equal. 0.177. Since that's 5 or bigger, 6 becomes a 7. So 0.177. Okay? All right, so before we can move any further, though, you have to make sure that you know how to use your calculator to evaluate these expressions, because that's going to be important when we talk about graphing and when we talk about some of the application problems in here. All right, so just make sure you can use your calculator with these things right here. Okay. All right, so that's going to take care of part 1. In part 2, we're going to look at starting to graph these exponential functions in part 2. All right.